Okay, so a 15-year-old has two pieces of information in trying to estimate the temperature in the backyard. One is the forecast high temperature from the newspaper. We will assume that this is normally the true temperature is normally distributed around this forecast with variance sigma 1 squared. And similarly, we'll make an assumption about the information from the backyard thermometer network that whatever you get as the average maximum temperature in the backyard, the real temperature is normally distributed around that, but with variance sigma 2 squared. So the question is, how are we actually going to get the variance of sigma 1 squared and sigma 2 squared? How are we going to estimate those? So pause if you want and think about that for a moment. Okay, I think what's natural here is that to do the one from the newspaper is that we keep a record over a previous sort of period of time. Okay, so we keep a record over a period of time, say for instance a month. Okay, and then what we would do is just take all of those sort of samples that we would get and subtract them from the actual temperature that the newspaper gave, right? So the newspaper actually gave an actual temperature and say they're indexed by K, and it gave a forecast temperature, so we can see this the next day, and then we take the sums of the squares of those. If we do it over a month, then we're going to go from sort of K equals 1 up to say 30, and then we would divide by 1 over 30. So that's basically a sort of sample covariance. And if we do it with a large enough sample, then we could, if there's no statistical bias, then we could imagine that the mean would be 0. Okay, for sigma 2 squared, then I think what we'd do is you'd just work for one day, right? So work on the data you have for one day over the whole network, and the fact that you've got all of these different thermometers at different places gives you different readings, right? So you could keep those, and then you could find the variance. You could find the variance from those, right, by the usual sort of thing, by finding their mean and taking the difference from the mean and the sums of the squares divided by the size of the sample. Okay, so that's a way you could, from the information, you could get sigma 1 squared and sigma 2 squared. Okay, so how do we go about getting the best information from these two pieces of information that we have, which is the forecast from the newspaper, and we figured out how that is distributed as a PDF, and the observation, we figured out how that is distributed. Well, the natural thing to do is to try to take a sort of weighted sum of these two things, right? Take the multiple of the TF plus some multiple of T0, the temperature you get from the observations. Okay, we call that the analysis temperature, TA. And I think it's sort of clear that alpha and beta have to be, the coefficients have to be bigger than or equal to 0, and they should sum up to 1. So if beta is 0, that means that you don't believe in the observation and the forecast is right, so alpha is 1. If alpha is 0, you don't believe in the forecast, so beta is equal to 1. So what are alpha and beta going to be? Somehow they're going to be weights that reflect your confidence in the two different measurements. So think for a moment about what alpha and beta should be. Well, the natural thing is that alpha should be proportional to 1 over sigma 1 squared, and beta should be proportional to 1 over sigma 2 squared, right? So if sigma 1 is very, very large, that means you've got very small variance in the distribution around TF. That means you really believe TF, right? So sigma 1 would be very small, so then alpha would be much bigger, right? So it's somehow alpha has to be proportional to 1 over sigma squared, and then by the same token, beta should be proportional to 1 over sigma 2 squared. Okay, so that seems very natural, but those don't add up to 1, right? So we're going to have to take alpha is equal to some constant over sigma 1 squared, and beta is some constant over sigma 2 squared, and then we're going to take the constant so that alpha plus beta is equal to 1. All right, so if you calculate that, you will see fairly easily that C has to be sigma 1 squared sigma 2 squared over sigma 1 squared plus sigma 2 squared. Right? And that then gives you expressions for alpha and beta. Alpha is going to be sigma 2 squared divided by the sum, sigma 1 squared plus sigma 2 squared. And beta is going to be sigma 1 squared divided by sigma 1 squared plus sigma 2 squared. Okay, so now let's think about the following as an interpolation, right? So instead of saying it's a weighted average, let's try to see if we can express it as the forecast plus something that we change to the forecast to sort of make it more like the observations. So we interpolate between the forecast and the observations. Just another way of saying this weighted average. Well, then obviously k has to be bigger than or equal to 0 and 1. So see if you can figure out what k should be given the alpha and the beta. Well, then it's clear that TA is going to be 1 minus KTF plus KTO obs. So K then has to be beta and 1 minus K has to be alpha. And you just have to check whether that is consistent, right? So K has to be sigma 1 squared over sigma 1 squared plus sigma 2 squared. Then 1 minus k, you can see easily, is going to be sigma 2 squared over sigma 1 squared plus sigma 2 squared. So this is beta and this is alpha, which works out just fine. Okay, now we're going to take a completely different approach and look at it as an optimization problem. So the idea is to sort of have a cost function which weighs up the forecast on the one hand and the observation on the other hand. So the natural thing is to take a quadratic function, a multiple of t minus tf squared plus a multiple of t minus t0 squared. The question is, what are the coefficients a and b? I'll leave you to pause for a minute and then think about that. Okay, well, what they have to be, A and B, A is going to have to be something to do with sigma 1 squared, and B is going to have to be something to do with sigma 2 squared, right? Because A is going to express your confidence in the forecast and B in the observations. If you think about it, though, A is going to have to be 1 over sigma 1 squared, not sigma 1 squared, because when sigma 1 is small, you should emphasize the forecast part. In other words, the coefficient A should be very big. B, therefore, is going to be 1 over sigma 2 squared. And those are exactly right. Okay, so the optimization approach says what we should do is to try to minimize this cost function. So we want to find, therefore, the minimum of j of t, and then the answer of the best estimate of the temperature, TA, we call it the analysis temperature, is going to be the argument of the minimum of j of t. So let's see if we can find TA. So I'll leave you to think about that for a moment. Okay, so since it's a quadratic in j of t, and you can see it's growing as t goes to plus and minus infinity, it's going to be a sort of parabola up. So the minimum is going to be found where you find the zero of the derivative. So we have to calculate j prime of t. So that is just 2a times t minus tf plus 2b times t minus to. Right? So obviously then, sorry, this is a, not alpha. So then we've got a times t minus tf plus b times t minus to is equal to 0. And it's the t that solves that, which is going to give us our minimum. Okay, so just a little algebra will tell you that t is going to be a over a plus b times tf plus b over a plus b times to. All right, so that's exactly the form of what we saw in the interpolation approach, right? A sort of weighted average of the forecast and the observations. So what you want to check is that a and b, given a is 1 over sigma squared and b is 1 over sigma 2 squared, agree that these coefficients agree exactly with our alpha and our beta. So you can check that. And it is indeed true. You can see that A over A plus B is going to be sigma 2 squared over sigma 1 squared plus sigma 2 squared. And B over A plus B is going to be sigma 1 squared over sigma 1 squared plus sigma 2 squared. So in other words, the interpolation approach and the optimization approach lead to exactly the same answer, right? So this is obviously the right answer.